Hello and welcome to yet another lecture on control system, paper code PCEE 503. Myself Prathita Roy, Assistant Professor of Dr. Sudhir Chandra, Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is root locus techniques. Lesson objective. After end of this topic, students will be able to construct root looking for simple systems and understand the stability of a system using root locus techniques. So we will start the root locus techniques. So the content, introduction, angle and magnitude condition, construction of root locus and examples. So we will start the introduction part. What is root locus? Root locus is a graphical representation of the closed loop poles as a system parameter is varied. So, in our previous discussion, we have seen the conception of route array. In case of the route array, we can only say that the system is stable or not. But we can't say how much stable the system is or the relative stability of the system. This relative stability of the system is obtained by the root locus method. It gives us the practical view of closed loop poles. So, it can be used to describe the performance of a system as the various parameters are changed. It gives graphic representation of a system's transient response and also the stability. We can see the range of stability, instability, and the conditions that cause the system to break into oscillation. So in order to find the relative stability of a system, root locus gives us an idea about how much the system is stable. It is known as relative stability of a system. So we'll start with angle and magnitude condition. So there are two important conditions that we need to know to obtain the root locus with the characteristics equation. We already know the general form of a characteristics equation is 1 plus GSHS equal to 0. So, GSHS will be minus 1. As we know that the S-plane is a complex plane, so we can write GSHS equal to minus 1 plus J0. This equation has a magnitude as well as the phase. So magnitude of GSHS will be 1 and it will be remain same for positive as well as the negative feedback. And the angle of GSHS will be plus minus 180 degree. Since minus 1 plus J0 point can be traced with the angle of plus minus 180 degree, plus minus 540 degree, plus minus 90 degree, and so on. So we can write the generalized condition of angle of GSHS equal to plus minus 2q plus 1 multiplied with 180 degree, where q is the value of 0, 1, 2. We put the values of q. When q equal to 0, it will be 180 degree. When q equal to 1, it will be 540 degree, and so on. So the general formation of the angle is angle of GSHS equal to plus minus 2q plus 1 into 180 degree, where q is equal to 0, 1, 2, and so on. So every point on the root locus will necessarily satisfy the magnitude condition as well as the angle condition. So purpose of angle condition is to calculate whether the given point that is lies on the root locus or not. And the purpose of magnitude condition is to calculate system A at any point which is on root locus. So the purpose of angle condition is to calculate whether the given point lies on root locus or not, and the purpose of magnitude condition is to calculate system gain at any point which is on root locus. So let us determine the gain at s equal to minus 3 plus j3. This is generally known as minus 3 comma 3 point at on the s plane, to the transfer function of GSH is equal to k s by s plus s. So we are putting the value of s, that is minus 3 plus j3, at that particular equation, and we will get that equation. From there, we calculate the angle and the magnitude for each part, and it will give the magnitude k angle 360 degree. The magnitude for that part is root over 80, and angle is minus 135 degree. Angle is 135 degree, magnitude is root over 80, and angle is 135 degree. For the second part, the angle is root over 80. The magnitude is root over 80, and angle is 45 degree. It is calculated by, in this way, the angle magnitude will be root over 3 square plus 3 square, that is root over 80, and angle is tan inverse b by a means tan inverse 3 by minus 3, that is tan inverse 1, and tan inverse 1 is minus 45 degree. So 180 degree minus 45 degree equal to 135 degree. And in this one, it is tan inverse 3 by 3, that is 1 and 45 degree, and the magnitude is root over 3 square plus 3 square, that is 80. So for that part, it will become k angle 360 degree, and multiplication will be done root over 18, root over 18, that is 18, and summation of these two angles, that is 135 degree plus 45 degree, that is 180 degree. So the angle became 180 degree because the angle is, how to calculate the angle here? It will be 360 degree minus 180 degree, that is 180 degree. And here 1 is an odd multiple of minus 3 plus j3. It is lies on the root locus. So the magnitude of the root locus we have already seen that the magnitude is given 1 and the magnitude value is from here it will be k by 18 equal to 1. So value of k is 80. So in this way we can calculate the magnitude and the phase angle of a transfer function. The system gain is the value of determining the system gain. So system gain is k equal to 80. So we will start how the conception of construction of root locus. So in order to do the construction of root locus, we have to follow some steps. Step 1 or the rule 1 is it is symmetrical about real axis. Rule 2 is that number of root locus branches equal to number of open loop poles and open loop zeros. Rule 3, real axis loci, that is a point on the real axis lies on the root locus if the sum of the poles and zeros to the right hand side of the point must be odd number. Root locus point will move on root locus path. So we all know that this is a S j omega plane and this is the real axis and this is the imaginary axis or j omega axis on S plane. So let us we are taking a number of, say the poles are lies on -1 for a particular transfer function. So this transfer function, this is given a transfer function is a s plus 3, s plus 4 and s plus 1, s plus 2. So from that numerator part, we will comment on the poles are lies on minus, from the denominator part that we will comment that the poles s plus 1 into s plus 2 equal to 0. From the denominator part, it will give that s equal to -1 and -2, that are the poles values, and s equal to -3 and -4, that are the zero values. So if I take a test point here, say here we are taking a test point, it is given that a point on the real axis lies on the root locus, means we will consider it is a root locus path, or we can also consider that it is a valid root locus path. If I take a test point on the real axis, if the sum of poles and zeros to the right hand side of that point must be odd number. So let us, we have taken a test point here. So on the right hand side, if I take a test point here, there is no poles and zeros on the right hand side. So it will be not a valid root locus path. If I take a point here, summation of the poles and zeros on the right hand side of that particular test point is only one pole is there. So it will be a valid root locus zone. If I take a test point here, there are two poles are lies on the right hand side. So of that test point, so it will be not a valid root locus path. If I take a test point in that particular area, so summation of all the poles and zeros, number of poles and zeros lies on the right hand side is 3. 1, 2 and 3. So this will be another valid root locus path. If I take a test point here, so summation of all the poles and the zeros that are lies on the right hand side of that test plane, 1, 2, 3, 4. So it will be not the valid root locus point. So in valid root locus path, so in this way, with the help of a test point, we can comment that which path is the valid and which path is not valid. Means when we draw a root locus will follow that particular path. It is given that root locus point will move on the root locus path. If this is a root locus path, the root locus point will move on root locus path. So another is the starting and ending point. The root locus starts at open loop pole with k equal to 0 and terminates at open loop zeros with k equal to infinity. So we have seen this is a root locus path. This is the valid root locus path in our discussion. So this is the starting of the root locus because root locus start with the open loop poles. This is the open loop poles. And a root locus start the direction that shows that a root locus that is start from there and it will end at open loop zeros. This is the open loop zeros. Here it is ending at open loop zeros. It start from here. It start from here. This is the valid path that we have already seen, and it is moved in this direction. But the value of k is the gain is 0, and here the k is infinity. Now it is start from that particular pole. The direction shows that, and it is now moving in that direction here and come and end and terminates at open loop zeros here and here. So this is the ending zone, and this is the starting zone, and this is the ending zone of the root locus. If I follow the directions, we will clearly see that it start from that two poles, it is rooted here, and it is ended at two zeros, two open loop zeros, and it start from the two open loop poles. So the rule 4 is to find the angle of asymptote. So the asymptotes that carries the root locus to infinity. So it is the root locus branches which terminates to infinity, means it carries the root locus to infinity. So number of asymptotes are the p minus j, where p is the number of open loop poles and j is the number of open loop zeros. So number of asymptote pole equal to p minus j. The angle of asymptote gives us the direction along which this p minus j branches approaches infinity. We will see it. So first of all, we will concentrate on the angle of asymptote. The angle of asymptote is given by q 2q plus 1 into 180 degree divided by p minus j. 2q plus 1 into 180 degree divided by p minus j, where q is 0, 1, 2, 3 up to p minus j minus 1. So the value of q is 0, 1, 2, 3 up to p minus j minus 1. So this is the angle of asymptote, and asymptote that carries the root locus to the infinity. Basically, asymptote that guides the root locus to infinity. And the number of asymptotes is given by p minus j. So the rule 5 is the centroid. So the centroid means at which the asymptotes are the real axis or the center of the asymptotes are known as centroid. So it is the intersection point of the asymptotes on real axis. So the centroid is the intersection point of asymptotes on real axis. On real axis, where the asymptotes are intersect, it's known as centroid. So centroid can be mathematically calculated as the summation of real part of poles of open loop transfer function minus summation of real part of zeros of open loop transfer function divided by p minus z. This is the way that we can calculate the centroid. So let us take an example. This is the open loop transfer function k into s plus t 3 divided by s into s plus 1, s plus 2 and s plus 4. So 1, 2, 3, 4, there are poles are lies on s equal to open loop poles are lies on s equal to 0, s equal to minus 1, s equal to minus 2 and s equal to minus 3. And open loop poles are there and the open loop zeros are s equal to minus 3. So you have to calculate the asymptote and the centroid of the following transfer function. So you all know centroid is the real parts of the poles of open loop transfer function, summation of all the real parts minus summation of all the real parts of zero of open loop transfer function divided by p minus j. So p is the number of open loop poles, here 4, and z is the number of open loop zeros, that is there 1, so p minus j will be 3. And the real part of the poles are 0, minus 1, minus of the poles are 0, minus 1, minus 2, and minus 4. The summation will be minus 7, and real part of the 0 is minus 3. So minus 7 minus 3, that is minus 4 by 3 is the centroid of that particular transfer function. So angle of asymptote we can calculate by the formula of 2q plus 1 into 180 degree divided by p minus j, where q will be from 0, 1 to p minus j minus 1. So p minus j minus 1 is 4 minus 1 minus 1, that is 2. So the value of q will be 0. The value of q will be 0, 1 and 2, because limit of q will be till p minus j minus 1, that is 4 minus 1 minus 1, that is 4 minus 2 equal to 2. So just putting those values here, we will get three values of angle of asymptotes, that is 60 degree, 180 degree and 300 degree for q value 0, 1 and 2, and p minus j value is equal to 4 minus 1, that is 3 for each case. For q equal to 0, angle of asymptote is 60 degree. For 1, it is 180 degree, and for 2, it is 300 degree that we have calculated. So here, the value of centroid is 4 minus 4 by 3. So it will be lies between minus 1 and minus 2. So this is the point of centroid, minus 4 by 3. So we have seen the three angle of asymptotes. So from here we will draw a 60 degree line. We will draw a 180 degree line, and another is a 300 degree line. And whether all the angle of asymptotes are intersects on the real axis, it is called the centroid. So from centroid we will draw a 60 degree angle, we will draw a 180 degree angle, and another is a 300 degree angle, and the asymptotes that carry the loop locus, to the infinity, and the intersection of all the asymptotes on the real axis is known as centroid, and it is clearly seen here. The value of centroid in this example is minus 4 by 3. So it is lies between minus 1 and minus 2 point, and it is clearly seen here with the centroid. So the rule 6 is to determine the break-away point. It is a point on root locus where two poles meet. One, the two poles meet, they split, that is, they break away from real axis. It is occur, the breakaway point is occurred due to the repeated roots at the same point, or the poles at the same point. So where we will find the breakaway point? If there are two adjacent open loop poles, there is a chance of breakaway point to lie in between the two poles. If there are two adjacent poles, if I see this example, there are two adjacent poles, one at 0 and one at -1. So there is a chance of breakaway point. Between these two poles, there is a chance of breakaway point if it is a valid root locus path. If it is here it is two poles, -1 and -2, there is a chance of breakaway point, but it will be a valid root locus path. If the two adjacent poles are there, in between the two adjacent poles, there is a chance of breakaway point. And the breakaway point that is occurs because of repeated roots at the same point or the poles at the same axis. So how to calculate the breakaway point? First, write the characteristics equation, that is 1 plus GSH is equal to 0. So arrange the characteristics equation in such a way so that k equal to fs. Differentiate k with respect to s and equal it to 0. Then we will give the valid and invalid breakaway point. So with the help of an example, you will see that how we can calculate the breakaway point. So it is clear that determine the breakaway point for the following transfer function is given. So we are just multiplying and we'll get a following transfer function. So on the root locus, the value of k GSHs will be -1. So we will put that value. So k GSH is equal to -1. So differentiating the k with respect to s, that is first order derivative of k, that is dds of k, means we are differentiating it with respect to s. So we will get the value of s equal to -1.45 and 3.8. So we will see that this is the breakaway point. From here, there is a chance of splitting that we have already told that once the two poles meet, the split, that is the breakaway from the real axis. So the poles are at -1 and -2. So the breakaway point must be lies in between -1 and -2. So from the two values of s, -1.45, that is lies between the -1 and -2. But 3.82 is not lies between the two poles, that is -1 and -2. So we can say that this is a valid breakaway point. So that's why we will call that differentiate. We have told that differentiate k with respect to s and equal it to 0. It will give us a valid and invalid breakaway point. So for that particular example, where the poles are lies at -1 and -2. So the -1.45, that is lies between -1 and -2, because we know that the breakaway point will lie between the two adjacent poles. So it is a valid breakaway point, but 3.82 is not a valid breakaway point. So this is the breakaway point, that is s equal to -1.45. And here the root locus is split from that breakaway point that we have seen in this figure. So rule 7, that is intersection with imaginary axis. This rule gives us point on the imaginary axis which the root locus will cut while moving to the right half of the S-plane. Intersection of imaginary axis can be found by using the Routh-Hurwitz criteria. Procedure to calculate the intersection with the imaginary axis, then the procedure are the, we first write the characteristics equation, that is 1 plus GSH is equal to 0. Then the construct the route array, determine the k that we have already done in our previous lecture in route array. We get the auxiliary equation. You already know that how to find the auxiliary equation in our previous lecture. Compute the root locus of auxiliary equation. this will be the intersecting point with the imaginary axis. So let us take an example in order to see the root 7. So it is given that determine the intersecting point with the imaginary axis with the following transfer function that is shown in the figure. From here we find the 1 plus GSHS equal to 0, and this is the characteristics equation that is given, that is to the power 4 plus 7s cube plus 14s square plus 8 plus ks plus 3k equal to 0. So in our previous lecture we have discussed how to construct the router. So in this way we all know that this s to the power 4, the coefficient is 1, 14 and 3k, and for s cube it will be 7 and 8 plus k. From the particular table, we can easily construct the router. We know in our previous discussed that how do we do the router. So for a square, s to the power 1 and s to the power 0, we will calculate the values of router. So from the router, it is seen that if this part, s to the power 1 part is 0, is the s. So the all the only s to the power 1 row can be all zeros. So for positive k, only s to the power 1 row can be all zeros from the router conception. So if this part is 0, it will give a value of k is 9.65. So the system is stable. So the system is stable when the k value is greater than 0, because all the sign in the first column of the route array will be same in order to. So all the sign for the first column of the route array will be same in order to find the system, or in order to say the system is stable. So the value of the k will be greater than 0 from here, and from here it is k will be less than 9.65. If k value is 9.65, it will be a square. This row will be remain also positive. So the value for the system to be stable, the value of k will be lies in between 0 to 9.65. So now the auxiliary equation, the row that is presenting to the 0th row, that one, that is 9 minus k square plus 21k equal to 0. Just putting those values of the k, we will find the values of s is plus minus j 1.59. It is the root locus which crosses the j omega axis at plus minus 1.59 j and a gain of 9.65. So with the help of a particular example, if this is the root locus, so it is crosses the j omega axis at plus 1.59 point. This lies between 1 and 2. And on the j omega axis, this is the j omega axis that we all know, and minus 1.59, this one lies between minus 1 to minus 2 point on j omega axis. So this is the crossing point or the intersection point on the j omega axis of the root locus, with a gain value of k equal to 9.65. So the rule 8, that is angle of departure or arrival, the rules that gives us the angle along which the complex poles depart or arrive from their original position. So the calculation for the angle of departure is given at angle of departure equal to 180 degree minus 5, or angle of departure can be calculated by the equation that sum over all the contribution of the angles by the zeros minus sum of all the contribution by the poles minus 180. And angle of arrival is given by the formula is phi a equal to 180 plus 5, and the angle of arrival can be calculated by the another formula called pi plus sum of all the poles, contribution of all the poles minus sum of contribution of all the zeros, that is the contribution of angle. We will see it by an example. We will see it our pole and a zero that is contribute an angle. So Let us determine the angle of departure from the following transfer function. So this is a transfer function where the poles are, the zeros are open loop zeros at s equal to -2 and poles are at -3, -1 plus j1 plus 1 plus j1. So why we choose the -1 plus j1 plane? So before going to the calculation of angle of departure, we will see that here the calculation are given in that way that here the poles are lies at -3, this is the pole, -1 plus 1, this is the pole, -1 minus 1, this is another pole. The three poles, there is a three poles. And the 0 at is equal to -2. So, when we calculate the angle of departure, if there are complex conjugated there in a particular transfer function, then the concept of departure will be arrived. If there is no complex pole in a system, so we will not concentrate on the, we will not calculate the angle of departure. So angle of departure is related with the complex pole. So here we are see there are two complex poles are there. One is at -1, 1 and another is at -1 point. So here are two complex poles are there at 1, 1, -1, 1 and another one is at -1, -1. So here the conception of angle of departure will be there. So the contribution, if I join those lines, means we are concentrate on -1, 1 pole. Just draw a perpendicular line here. This one. Again join these two poles with the help of this line and draw a perpendicular here. Means we are joining -1, 1 and -1, -1 poles with the help of this straight line. And we are joining the -3 and this pole, that is -1, 1 pole with the help of a green line. And we are joining the -2 and -1, that is the 0 at -2 and -1, -1, pole, that one with the help of a yellow line. Just joining this with this one with the help of a green line, this one with the help of a yellow line, and this one we are joining here. And so phi 1 is the contribution for the pole 1 with respect to this point. Phi 2 is the contribution of pole 2 with respect to this point. Phi 3 is the contribution of 0 with respect to this point, and phi 3 is the contribution of pole 3 with respect to this point. So what is the value of phi 1? It is clear from that equation, the contribution for the poles, that is phi 1 is equal to 0 degree. And what is the value of phi 2? It will be clear from that picture, it will be 90 degree. So another pole is at -3. Phi 2 will be 90 degree, it is clear from the picture. And another is the phi 4, that is called the number 3. So what is the value of phi 4? This value will be 1. And this value, the base will be 2, because it will be -1 minus of -3, that is 2. So this base value will be 2 and this value will be 1. So the phi 4 will be tan inverse 1 by 2. It will be give 26.56 degree. Tan inverse 1 by 2. So contribution for the pole, that is phi 3, it will be, this value is 1 and this value is 1. That is -1 minus of -2, that is 1. So phi 3 will be tan inverse 1 by 1, it will be 45 degree. So how to calculate the angle of departure? Pi d. It is contribution. It is sum of contribution of all the zeros, that is 45 degree, minus sum of contribution of all the poles, that is 0 degree plus 90 degree plus 26.56 degree minus 180 degree. So this is the general formula to calculate the angle of departure, and it will give minus 251.56 degree, and this is the value of, from here this is the value of 251.56 degree. This is called the angle of departure. So in this way we can calculate the angle of departure. So that is why in this equation we take the s equal to minus 1 plus g1 point and putting those values and taking the that we in our in this discussed we have calculated how we can find the angle and the magnitude of each part, and from that we will find the values of angle and magnitude, and it is clear that this angle, that is the contribution of the zeros, that is 26.56 degree, 0 degree and 90 degree, that we have already seen. This one 0 degree, 26.56 degree and 0 degree. The conception of 0 will be put here. It will give the contribution of the 0, open loop 0, it will give 45 degree, that we have already seen. The 45 degree. So the angle became minus 71.56 degree. We know how we can calculate this. So angle of departure you can calculate in another way. That is 180 degree minus 71.56 degree. That is 71.56 degree. That is 251.56 degree. So it will be calculated in this way, that 0 plus 45 degree minus 26.56 degree plus 0 minus 0 degree minus 90 degree. So summation of this angle minus summation of these two angles, they will give the values of the total angle. So summation of the angle and summation of the angle at the numerator and the denominator part, that is 0 plus 45 degree minus 26.56 degree plus 0 degree plus 90 degree will give the minus 71.56 degree, and 180 degree minus 71.56 degree, that will give 251.56 degree. That is the plus minus 251.56 degree will give the angle of departure, and this is the angle of departure that we have already seen, and we know this portion that we have already discussed, and this is the angle of departure. And when we draw a root locus, it will follow the angle of departure. Say, so say we have drawn a root locus like that. So this is we have told that when a complex pole is there, it will be give angle of departure. Say we have angle of departure of say 60 degree. So we will draw a 60 degree from here, minus 60 degree. Say, and we will draw a plus 60 degree from here. Say angle of departure is 60 degree. Now, when you try to draw a root locus, if I draw a root locus, the root locus will follow that angle. The root locus will follow that angle, and it will follow the asymptotes also. So when you draw a root locus, it will be like that. If the asymptotes are like here in this way, if I say the asymptotes are like in this way, so root locus will be, and the angle of asymptotes are like in this way. So the root locus will follow the angle of, say this is the angle of asymptotes. and root locus will follow the angle of asymptotes. So it will follow the angle and it will move in the direction of angle of asymptotes and also follow the angle of departure. Because angle of asymptotes that is carrying a root locus to the infinity, and it is clear that the root locus is going to infinity in the alignment with angle of asymptotes, and it will follow the angle of departure in order to move to the infinity. So this is another portion of calculation of angle of departure. So let us take an example in order to a feedback control system. It's an open loop transfer function. It is GSH is given by K by S into S plus 4 S square plus 4S plus 20. Plot the loop locus for K equal to 0 to infinity. So here number of open loop poles are 4 and number of open loop zeros are 0. So the poles are at 0, minus 4, minus 2, plus minus J4, and number of zeros are 0. So angle of asymptotes that we can first calculate, that is 2q plus minus 1 into 180 degree divided by E by Z. That is 2q plus 1 into 180 degree that we have already seen divided by E minus Z, and range of the q will be up to 0, 1, 2, E minus Z minus 1, that is 4 minus 0 minus 1, that is 3. So 0, 1, 2, 3. For each values of q equal to 0, 1, 2, 3, we have found the angle of asymptotes are 45 degree, 135 degree, 225 degree, and 315 degree. Now we calculate the centroid. Centroid will be the real parts of the open loop poles of summation of real parts of poles of open loop transfer function, that is 0, minus 4, minus 2, minus 2, that is minus 8, minus real part of zeros of open loop transfer function, that is 0. So minus 8 minus 0, that is minus 8, divided by pole minus 0, that is 4 minus 0, that is 4. So minus 8 divided by 4 equal to minus 2, the centroid. So there are two consecutive poles or lies, so there will be a chance of breakaway point. So the breakaway point we can find with the help of this equation, GSH is equal to minus 1. From there we can find the K values, and on differentiating the K with respect to S, dkds, we will find the values of S will be minus 2 plus minus J 2.45. So from that two equation, there are three roots. So S equal to minus 2 is definitely a valid breakaway point and lies on the loop locus. So this point is lies on the loop locus, and it is a valid loop locus, valid breakaway point. So we already know how to determine the valid and invalid loop locus point. So there is a calculation of angle of departure because there is a complex poles or lies there. We have already seen that how we can calculate the angle of departure, whether the contribution of poles or zeros, contribution of angles for the poles and zeros are there. By using that same conception, we will calculate the angle of departure and putting the values of S equal to minus 1 plus J1. So the angle of departure became 270 degree. So the intersection with the imaginary axis is the characteristics equation that we can easily form, and from the characteristics equation we put the route table, and from the route table it will clear that when the value of k is greater than 0 from that particular part, and again the value of k less than 260 degree from that particular equation, it will give the system to a stable one to make all the sign of the first column of route array positive. So for the marginally stable, the values of k will be 260 degree. For marginally stable, this portion will be 0. The values of k will be 260 degree for the marginally stable or marginally stable system. Marginally stable system, the values of k will be should have rows of zeros, so values of k marginal will be 260 degree. So in this way we have drawn the root locus. We know how we can, first we find the valid root locus path, then we will find the centroid, and from the centroid we will draw the four values of the centroid will be lies on here, that is s equal to minus, the centroid will be at -2, and it is also a breakaway point also. So s equal to -2 is a centroid and also a breakaway point. It is the centroid is at s equal to -2 and the breakaway point is s equal to -2. So the this is a say the -2 point, which is a centroid, and from here we can easily draw the angle, that is 45 degree, 135 degree. Means first we draw the 45 degree here, then 135 degree means we will be rotating this direction. We will be rotating this direction, that will be 90 degree plus 45 degree will be 135 degree. We will be rotating the direction, means the anti-clockwise direction, to draw the 135 degree. Then from 135 degree we will draw the 225 degree. 225 degree means if I draw a 45 degree angle there, it will be 180 degree plus 45 degree, it will be 225 degree, and another is the 315 degree. We will draw the 315 degree in that particular manner. So in this way we can easily draw the 45 degree, 45 to 95 degree in the anti-clockwise direction. You can easily draw the values of angle of asymptotes that we have already seen. This one. And this is the breakaway point, means there is a chance of the root locus to split from the breakaway point. So another is the third part is called the angle of departure that we have calculated at 270 degree. So by following that angle of departure, we will draw a root locus. This is the root locus that we have drawn, and it is follow the angle of asymptotes, because this is the angle of asymptotes line, and it carries the root locus into infinity. 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 And here there is a split of the root locus at the point of breakaway point, and the values of marginal stability, for that the gain value is 260 that we have calculated, and also the point of intersection that we can easily be calculated with the help of that we have already seen, that how we can easily calculate the DKDS value to find the point of intersection on the imaginary axis, this one and this one. So in this way that we can easily construct the root locus. So today we have already discussed about the root locus technique and how we can able to construct the root locus, and how we can comment on the stability, that is stable, unstable, or marginally stable our system is with the help of root locus technique. Thank you.